Yes. First incompleteness theorem. And I just realized that I forgot to put a slide for the second incompleteness theorem, but I'll tell you what it means in a second. I don't know what's going on. I mean, my mind is like a sieve. Not sieve of Eratosthenes, but some other very leaky device. First incompleteness theorem. If you have a consistent theory which includes Peano arithmetic, natural numbers, any consistent theory has a proposition which is true but not provable. It's a paradoxical thing. It's true, but cannot be proved with the axioms. Right? It's a stronger statement than to say there is unprovable proposition. Because you could say, well, it doesn't matter. No, this proposition is true. It's true in some fundamental sense, in the model, but it's not provable with an axiom. So this is a very paradoxical thing. Observe that it starts with a consistent thing. That is, because our proof will actually say that, as you will see in a second, that if it's inconsistent, it could be complete. But if it is consistent, then there is such proposition. So consistency forces incompleteness. Contains a proposition which is true, but which is not provable. Okay? By the way, while I'm here, and before I forget, let me tell you what the second incompleteness theorem says, because it's very related. The second incompleteness theorem says that you cannot prove consistency of a theory containing Peano arithmetic from itself. That is, you need a more powerful theory to prove the consistency of that theory. As you see, this is not a good path, because you see, Hilbert was trying to say, let's take smaller theory and prove the consistency of a bigger theory. Now, Gödel proves that to prove the consistency of a smaller theory, you need bigger theory. And big theory, is it consistent? Yeah, you could prove its consistency in even bigger theory, adding more axioms. And it goes on forever, which doesn't add confidence, it seems. So these two things sort of seemingly put a stake through the heart of Hilbert's program. Of course not. In reality, there are many important things which followed from Hilbert's program. But let me quickly, again, I struggled for a week trying to figure out how much I should tell you about the proof of Gödel's theorem. And I decided to give you a one-line proof, or a very abridged proof, because a lot of it is quite technical. It's just writing, representing propositions as numbers, doing utilization, all of this stuff. It is actually tedious. But what's the idea? The central idea is that first you could represent propositions as numbers. So then, since propositions becomes numbers, in your theory, in Peano arithmetics, you could write predicates about propositions. Because a predicate on number could refer to a proposition which is encoded by this number. Then, of course, you could build a program to generate proofs. He has recursive functions, and for you it should be fairly self-evident. I mean, you just encode inference rules as functions which return other numbers, which is propositions, during this encode. You go and you go through all this machinery, but what's the central point? The central point is that you want to generate a certain magic proposition, the proposition. And that's the proposition. That is, you want to write a predicate which applies to itself and says, this proposition is not provable. And all this technical machinery actually shows you that you could write this proposition. This is all it does, that you could write proposition with the following meaning, that this proposition is not provable. Now, is it true or false? Well, let us think. If it is false, it's either true or false. We all buy, which again, I don't know why we buy into that, but we do. We say that any proposition should be either true or false. It's either true or false. If it's false, it is provable. So we managed to prove a false proposition. What does it mean? Our theory is not consistent. Therefore, the second alternative, it is true. But if it's true, it is not provable, because that's what it states. That's the plain meaning of the proposition, which we wrote with great difficulty, is that I am not provable. So if it's true, it's not. So if it's false, your theory is not consistent. Otherwise, if your theory is consistent, it's true. Right? And that's what, if we look here, this is what it says. If consistent, it has such proposition. And we write this proposition. So Gödel's theorem, again, what does it remind us? It reminds us of all these paradoxes. But the same, after the last lecture, Panam comes to my office and he says, this proof of Cantor's theorem that a power set is more powerful than a set, it's not satisfying. There is something fishy about it. Of course there is something fishy about it. But that's the proof. Of course, when you do these self-referential things, there is something unsatisfying. But as we shall see, a large body of mathematics and theoretical computer science is based on things like that. That's just a fact. Whether it satisfies you or not, that's another story. So this proposition is not provable, is the magic proposition on which the entire Gödel theory is founded. Yes? Everything else is just technical, how to write this proposition formally. Right? But that's the proposition you write. Now, we have to get to a much more cheerful guy, Alonzo Church. A nice guy. Doesn't he look like a nice, well-adjusted guy? He's from old Virginian family. He is very charming, especially with men. He doesn't socialize with women and manages that when he graduates from Princeton, he is a Veblen student, he graduates from Princeton and voted to be the least likely to ever get married. And immediately gets married. He was this charming guy who was but not a drinker. He is, again, practicing Presbyterian. So he's a Presbyterian. And a very formal but he's by the way, I'm sad to see that Bert Anderton is not here, because probably he could have told us some personal stories about Alonzo. His father happened to write the best little biography of Church as a forward to Church's collected works. And there he says, among other things, that he was extremely likable old Southern gentleman who would always be courteous and polite and just very, very nice. And indeed, a very great figure. So he's this guy at Princeton who starts studying this European work, and then Gödel starts coming to Princeton. So Church realizes that there is a field here. It's not just an individual result, but all this stuff, the notion of recursive functions, which he discovers independently. He discovers almost at the same time as Gödel a formalism called lambda calculus, which is equivalent to recursive functions. But he observes generalization, he observes all this formal notation, and he says there is a new field. And the field is called symbolic logic, mathematical logic. You take it for granted there is a thing called mathematical logic. You might not know what it is, but you know that it is there. At that point, nobody knows. Somebody has to say there is a field. And what do you need to form a field nowadays? You need to do two things. You need to start a professional organization and an academic journal. And that's what he does. One of the great accomplishments. Well, and of course, you need to have a bibliography. So at the same time, in 1936, when sort of Gödel comes, gives talks, Church sits down, and he's a wonderful guy. He knows every language under the sun, or at least every language in which anything mathematical is written, plus Latin and Greek. He writes this wonderful thing called Bibliography of Symbolic Logic, a very major, sadly enough, out of print. And then he says, well, and we will found the Association of Symbolic Logic and elect somebody very appropriate as the president, himself. But he is really the most appropriate person, no question. And let me tell you, this is the guy, he combines this great stature with lack of ego. It's not about him. It's about creating the field. So he was just the right person. He was the right person at the right time. So he created the association and starts a journal of symbolic logic. And then what do you do next? Finally, you need to have a textbook. And some of us remember the textbook. Church, right? Like this book, Introduction to Mathematical Logic, for many of us was the book. There was nothing else. Later on, some of his students wrote other books. But when he writes in 1944 this book, that's the book. There is nothing else. The first book you could teach a course. You cannot have an academic discipline without a textbook. So the man is absolutely astonishing being able, and he's dedicated to it. Forever he remains at least partially an editor of, first he edits the papers, then he becomes a more important job, because the editor of the review sections. That's very important because he reviews every article. He assures that, well, not personally, that somebody reviews every article in symbolic mathematical logic and says, this is good, this is bad, what you should read, what you should follow. Amazingly important thing. He stays forever at Princeton, forever. In the 60s, however, Princeton indicates that when he retires at Princeton, has a mandatory retirement age at 71, they will not keep any of the staff of Journal of Symbolic Logic, which for him is a tragedy. There's just a couple of people, but I mean, the thing will collapse. So he's prepared to do something unbelievable. Church decides to leave Princeton. You have to understand that he went to Princeton, he was a Princeton man, that was his life. And when he is old, he is like my age, he decides to accept an appointment at UCLA. UCLA is very clever, decides to attract Church with the Journal of Symbolic Logic and builds one of the greatest programs in mathematical logic. Again, I'm sad to see Bert not being here because he would be able to testify at least secondhand from what his father was one of the original members of this great department. So Church goes there and keeps teaching. This is sometimes I think that, you know, I should stop teaching at 6 months because I'm senile. Okay. He keeps teaching till he turns 87. 87. And by all accounts, beautiful lectures. Very good. So, amazing gift. Publishes his last paper the year he dies. And he dies in the ripe old age of 92. I mean, you know, I do not think I'll be writing papers when I'm 92. So, an amazing guy. And sort of leads very balanced life. Wife whom he loves very much and who is wonderful cook, so he invites other logicians, mathematicians, other people to eat at his place. Has 3 well-adjusted children. You know, sort of just a wonderful, wonderful guy. And he creates the great school of mathematical logic. Sort of the thing which you need to know is his students. He has 31 students altogether, but look at the list. Anybody who knows anything about logic? Well, if you don't, these are the names. If you don't know who Alan Turing is, I don't know what you should do with yourself, but you should know. So, Kleene is his student. Rosser, Turing, Henkin, Martin Davis, Hartley Rogers, Michael Rabin, Dana Scott. The last 2, the least significant. Both of them won Turing Awards. Just these guys who dropped into computer science because they couldn't cut it in mathematical logic. So they become the best computer scientists we got. So not bad. The other guys, there are a bunch of other guys who I could, like Raymond Smullyan. Some of you might have read his popular books, which are quite good presenting. Much more recommended than Hofstadter. And he was Church's student. No, Smullyan. Okay, so he creates, and then, like everybody, sort of, if you start looking down, everybody you know goes back to Church. Like some of you might know, even personally, my friend Dave Masser. I have this friend with whom I worked closely for 30 years, and we wrote books and papers together, and he's my closest friend. Well, he is a student of who invented garbage collection? George Collins, thank you. He's a student of George Collins. I know George. This is truly shameful. Not of George. I mean, you know, I shared an office with him. So he's a student of George Collins, who is a student of John Rosser, who is a student of Alonzo Church. So everybody in this field comes from, you know, like if you go, like half of computer scientists are students of Constable at Cornell. Seems that like half of the population. He's Ross's students too. So I mean, they all, and you know, there is this remarkable, and this is why I could, because of Church, I could say that mathematical logic is the only truly American mathematical discipline. In a sense, in spite of the fact that it was invented by an Austrian, it became a science in the United States. And thanks to Church and his students. Of course, Stephen Kleene is a remarkable guy. I mean, again, for older people. What did he invent you use every day? Regular expressions, guys. You know, some of you use regular expressions, maybe. You know. So he invented regular expressions. So there is practical use in mathematical logic. And there is, of course, the third name on the list, which is not bad. So Alan Turing. And that's, well, before we talk, that's where we're heading. So we need to talk about Church's thesis. You see, Church came up with something unprovable, but which is fundamental thesis on which computer science and logic is based. This is known Church's thesis. Some people call it Turing thesis, but because more people know about Turing, but Church was the first person to state it. Let's assume you have a formalism for doing computation. It says lambda calculus, or recursive functions of Gödel, or Turing machines, or Markov algorithms. There's this guy Markov in Russia who comes, or post system. I mean, they're all these systems. Which one is better? Who knows? But then comes Church's thesis. He says they're all equivalent. That whatever systems we have and whatever systems people might invent will always be equivalent. Whatever is doable with Turing machines will be doable with this new. Could we prove it? No. Why couldn't we prove it? Because we're quantifying over non-existing things, future things. We're saying whatever formalism will come in the future. I mean, we could prove that Turing machines are equivalent to, say, lambda calculus. People did. But then say, well, they're both inferior to this future system I will design. Church says no. Whatever could be done with one could be done with the other. That these systems fully capture the notion of effective computability. Right? This is sort of the foundation. And you say, but you take it on faith. Yes, guys. This you have to take on faith. It's not provable. Right? But it's central to everything we do. It's in other words, whatever you could do on a PC, you could do on Apple. Let me restate it. Or whatever you could do, maybe slower, but like, you could do the same in Python than in C++. Again, it might not run as fast, but you could pretty much do the same stuff in every programming language. Yes?
And does quantum computing model fits into here?
So far, there are no examples of, even assuming, I'm not saying there are no quantum computers, but what I'm saying, we do not have any algorithm which is realizable on quantum computer, which is not for some undecidable problem. You could do decidable propositions faster, right? No, but that's, I mean, that is true even with these other models. Obviously, most of modern computers are a little faster than Turing machine. Why?
But you could, in a finite time, decide.
Yes. So far, there are no undecidable propositions. This is, again, Church thesis still stands. There is no mechanism, not even realizable, but sort of, Turing didn't actually build a Turing machine. I don't know whether you know that. I mean, he had difficulty finding infinite tape in stock. But Turing machine is, in some sense, very slow because it doesn't have random access. You have to go through the tape step by step. We'll talk about it. So Church's thesis is a very, very powerful thing, which we always need to keep in mind. That sort of, and then, in some sense, there is another important thing, which says that all this stuff about programming language is much exaggerated. Which is, there's just so much you could do with programming language. I mean, it's not going to make unsolvable problems solvable. Right? But that's just off-the-cuff observation. Alan Turing. You realize that now is this very special year. And all the world, except for A9, celebrates 100-year anniversary. There are parties. There are truly parties. It's a big deal because while, again, I don't think, I mean, as always when there is celebration, people tend to exaggerate the importance of a person they celebrate. That is, he was part of this genius generation. Right? I cannot say he was a greater man than Gödel. He wasn't. Or greater man than Church. It was just a remarkable thing that at the same time, a bunch of extremely brilliant people came out in this field. Turing was one of them. Very brilliant. Do not misunderstand me. But right now they sort of, make all kind of stories. Then tells me he goes to a museum in England and say, oh, you know about Apple computer. It's named after Turing's apple because, as you all know, he bit on an apple which was poisoned. They don't know whether it was poisoned, but that's the apple after which Apple computer was named. Steve Jobs, actually, when asked, answered very nicely. It's false, but I wish it were true. In any case, so right now he invented everything. He invented Apple computer. No, but he was a genius. No question about it. Young Cambridge guy, Clare College. eventually sort of starts working on all this stuff we're talking about, and goes and spends time at United States, which was very good, with Churches as his advisor, writes a brilliant thesis, gets a PhD. What is his work? Invents Turing machine, comes with an example of an undecidable proposition which cannot be, again, decided or solved with a computer, which is halting problem. We'll deal with halting problem. Introduce a notion of Turing completeness. This is equivalence of Church's thesis. It's sort of the same. I mean, some language or formula is Turing complete, means you could do everything in it. It's like with Turing machine. Then works on secret establishment, doing decoding. We still do not know what he actually did. Stuff is still classified, which is pretty remarkable, but you know how spooks are. After the war, he sort of becomes a lost soul. He does not, I mean, again, he has no students, never gets engaged, does work on what we would call AI, and thus found AI, the notion of Turing test. You know what Turing test is, a test which distinguishes between me and computer. Yes, computer doesn't forget. No, it wasn't the test. The test is actually you talk through the wire and you say, this is Alex and this is some computer. This is called Turing test. And apparently does some very significant work in biology. Some of it is not published for decades. But again, I didn't know. Dan told me about biology. Clearly remarkable guy, but a loner, not very well sort of adjusted, lives sort of by himself, gets into, do you know how he, well, for those, just one sentence, for those who don't, he's gay, but he's not one of the gay people who are very popular in the gay crowd. He has to go pick guys in working class, boys in public lavatories. That's not the best way, even for a heterosexual person to pick people. So he picks some teenage fellow who is a criminal, who robs his house. And he goes and reports it to the police, saying, well, I picked up, you know, so this is at the time a criminal offense, soliciting in the public bathroom. So he reports himself to the police, gets arrested. They tell him to take hormones to sort of control his sexual urges. And some people say because of that he gets depressed, and there is a theory that he doesn't get depressed, but experiments in some chemical stuff in his room, nobody understands, but gets cyanide poisoning and dies. 43 years old, sort of, if he lived till Church's age, would have done great things, but died. Great tragedy, and a very, very great man. Yes?
I would be tempted to put one more line in there. Right around the time when von Neumann was designing, modern computers, Turing also wrote a report, and I mean there was mutual collaboration, but his report was an incredibly good one. It was not what they got. It was what led to the Pilot Ace, and it talked about the basic computer architecture and also a lot of early underpinnings for systems programming. So,
yes, this stuff Paul knows. I do not. Again, I know mostly about his logical work. So let me just sort of. I need to know more. You need to know more. Go visit computer museum. Let me put there. I'm sure there is some. Or send a link. Yes, and I'll put it. Yes. So now, here we come to doing real proofs. Now it's going to get mathematical. Diagonalization. Well, not right away. Diagonalization. What we observed is that Cantor's proof, the idea of sort of looking back at yourself, diagonalizing, becomes a center of whole things. A bunch of results in logic and computer science come from that. And by the way, Cantor didn't invent it. I have to quickly mention Lias paradox. It all goes back to a long, long, long time, where Epimenides, a Cretan philosopher, says all Cretans are liars. Is his proposition true? Sort of, again, people discovered that this constitute paradoxes, and in the Middle Ages there are several wonderful logicians who work on it. So they reduce it to a proposition: what I'm saying is false, which causes trouble. Whichever way, I mean, it's like, have you stopped beating your wife? It's difficult. What I'm saying is false. And there was a remarkable work by Bradwardine at Merton College, and Jean Buridan, a great rector of University of Paris, Sorbonne, who also invented famous Buridan's S. I don't know what Buridan's S is. It's a very marvelous logical device. It's an S who equidistant from two piles of hay, and he starves because he couldn't make up his mind. Buridan's S. Freedom of choice sort of question. So, but let us try to do, I will not dwell on history, let us try to look at whether we could find a generic proof of Cantor, of diagonalization. Whether we could construct something which will solve all diagonalization things in one fell swoop. Right? And why it's good? Because you see, this we will do exactly what we do when we abstract generic code, except we're doing it with a proof. We'll try to find the most general representation of this argument. And let us see how we do it. Well, first of all, we start with, here we have to do boring mathematics. But the intuition is we want to come up with the weakest possible condition for what we do. And the weakest possible condition, we say that, well, first of all, we're going to have some family or set of functions, possibly partial functions. Don't have to be total functions. Partial function is function which is not necessarily everywhere defined. Which has one or two variables. One or two. Could be three. You could include 3, 4, 5, 6, 7, 8, all the way up to 95. No, all the way up. But I'm not going to use them. Therefore, I'm not mentioning them. I'm saying this is not a limitation of my proof. If you say, but in my family, I have functions of 7 arguments, like most functions in our search engine have 7 arguments because, and it will work here. So let us look at the example. All the total functions from integers to integers, or from pairs of integers to integers. Are they? It's a family by definition. They're not. By the way, what is so remarkable with this definition? What is lacking? What is not here? There are no axioms. Oh, by the way, I said you can have 0 arguments too. Doesn't bother me. I will use only 1 and 2 for the following. But there are no axioms. I'm not even saying just some functions with 1 or 2, with 1 or 2 variables. All functions? No, just some functions with 1 or 2 variables. So this is very general as it comes in some sense. Yeah? Then I come with this amazing definition. And we have to dwell on it a little bit. I define an interpreter. What is an interpreter? An interpreter in the family is a binary function. This is Gothic I. I have to impress you with my typesetting, but it also looks beautiful. You know, this old Gothic. You know. Gödel would have died for it. You know. So this I is an interpreter if for every unary function there is C, pronounced as code, such that for every input, interpreter of code and input does whatever this function does for this input. Interpreter, yeah, an interpreter. So the difference here, of course, I'm not telling you how you find the code. The only thing I say, there is. You know. So I don't have to, you know, implement it or anything. I say, if it exists, it's called an interpreter. Everybody agrees that it's sort of a very generalized notion of an interpreter. Take code, input, and do whatever any function f does. Right? Paul gets it.
Yeah. The one slightly weird thing, but not so weird, is that you have to, the code has to be from that very same type as the data. But we're kind of used to that in our...
Yes, because it has to be bits. If you have bits here and bits there, it's all the same. Or S expressions we will encounter very quickly in Lisp. You know, S expression here, everything is an S expression, by the way, in Lisp. Right? Or integer, if we live in the Gödel's universe. Right? But that's very important. Observe that unary-binary family was requiring the same inputs for binary functions. That was a requirement. You will see why. I could tell you why, because I want to diagonalize, and I cannot diagonalize unless they are of the same type. This is just, I really couldn't carry the proof when we come to the proof, unless they're the same type. If you give two different types, I am doomed. So I have to demand, right? So everybody follows. This is, if you don't, look at the slide. This is worth getting. Now, example of an interpreter in Lisp. In Lisp, we have eval. Eval is slightly wrong for us because it takes one argument. Let's take two argument eval. I call it eval 1. It should have been called eval 2 maybe, because it takes two arguments. But for those of you who remember common Lisp, I'm defining a function eval 1 taking two arguments. You don't put a comma in Lisp. It's all. And then what do? You eval cons xy.
Apply. That's called apply. Apply. Yeah.
Yeah, it's called apply, but eval, it works. You know, I'm using eval as my thing. Apply actually takes a function, not an S expression. Takes two S expression, treats first as code, the second as data. Right? So this I'm just showing that it's in our world, and you could write, you know, sort of an interpreter for C++. Or I'm not sure about Java. But yes, you could do it even for Java. So another interpreter. Let me show you another interesting interpreter, totally from a different domain. Let's take a unary-binary family containing functions x plus k. X is a variable, k is a constant. And also it contains these guys and these guys. X plus what? Plus k, some constant. Then we have an interpreter for our unary functions. Don't forget, I don't need to interpret binary functions. I just need to interpret unary functions. So W of 0, which is x plus y, is an interpreter for all the unary functions. It just is. You say, it's not a very powerful interpreter. I'm not talking about powerful interpreters. I'm saying that it's an interpreter in our family. I just want to show that it's very, very now. And here we come with utterly weird idea. We come with the notion of an anti-interpreter. What's an interpreter? Interpreter which for every function it could do what it does with some code. Yes? anti-interpreter. It's for every function. I could do something else. Right? It's just whatever he does, I'm not going to do it. I'm going to do something else, which is I will do something totally opposite, just out of spite. And it seems to be, you know, even easier thing, because he's going to be computing, Paul, say, square root. And I just have to do something else. Like I have to return, I'll be returning 3 for every number but 9. And at 9, I'll return 5. So my code is much simpler than his code. But it is an anti-interpreter, right? Or for this particular function. Right? So, by the way, in terms of, I call it, this is Gothic A, anti-interpreter. And also demonstrates my great abilities with LaTeX. So, and what's the change in the axiom? Well, the change is that you cross equality. So whatever he does, I'll do better. There was a song. So, yeah, there was a song. Okay. So let us see an anti-interpreter. For example, in this family L, there is an anti-interpreter. Right? We could take x plus y plus 1. And then for every k, I'll just plug it there. And obviously, it will be 1 different. I'm just doing whatever the interpreter did plus 1. So it will do different thing. It's an anti-interpreter. Huh? Good enough? Just fine. Very simple. Now, eval, by the way. Could we make an analogous anti-interpreter for Lisp? Anybody knows? What if we just add 1 to whatever? Think about it. You will know the answer by the end of the thing, but the answer is no, by the way. But you couldn't make an anti-interpreter. But let's see why not. So you could make an interpreter. This is the astonishing thing. We wrote an interpreter, but we cannot make an anti-interpreter. And let's see this thing. First of all, we come up with a new definition. You know, it's always you pile definitions. This is called mathematics, piling useless definitions. So unary-binary family is called diagonalizable. What does it mean? It means if you have a binary function with 2 arguments, I could feed the same input to both and get a unary function from the same family. So if G is in my family, then I could plug x and there is a function f in the family. For example, if I have function multiply, I'm going to have a function square. If I have a function plus, I'm going to have a function double. Simple stuff. So this is the condition. And you say, but it's always true. Yeah, it's always true. This is why it's almost always work. Except we will see an example. It doesn't always work. There is a diagonalizable family. This is diagonalizable. Obviously, in Lisp, S expression is S expression. You could pass it to, you know, if you have a function with 2 arguments, I could make a function of 1 argument. It's trivial. But remember our, where is it? I'll get to it. I forget the order of slides, guys. Apologize. I told you I'm an old and stupid. Anti-interpreter. Diagonalizable family does not have an anti-interpreter. A very general statement. That if you're diagonalizable, you never, ever will have an anti-interpreter. You might have an interpreter, but not an anti-interpreter. It just never exists. Right? This is the deepest theorem there is, because it covers all kinds of computer science, mathematics, and mathematical logic. And how do we prove it? Very complicated proof, 1 line. So let's assume that there is an anti-interpreter. Then let us take its diagonal. Anti-interpreter is big Gothic A, therefore we'll call its diagonal small Gothic A. Make sense? Could we do that? Yes. And since our family is diagonalizable, this guy is in the family. Everybody agrees? It's just because it's diagonalizable. And then we know that since this big guy, A, is an anti-interpreter, there is code which will do something that A of x will not be equal interpreter, anti-interpreter C of x. This is definition of anti-interpreter. I just plugging in things. But then observe that diagonal of anti-interpreter is equal to the diagonal anti-interpreter. And diagonal at this point is not equal. Contradiction. We just take the diagonal, find its encoding, plug its own code into it, and get contradiction. You say it's not deeply satisfying. I warned you, Perham said so. That is, but it's the most general way of doing these kind of things. We just say you could never have an anti-interpreter as long as you have diagonalization. Right? And you need to dwell on it. You say I don't get it right away. Well, it's just it's one of this. It's like liar paradox, except it's not a paradox. It's a real proof. All right? And how about L? Do you remember L? The guy with linear functions? It had both interpreter and anti-interpreter. But it is not diagonalizable. Because if we take function, binary function like that, xy, and diagonalize it, we get function like that, which is not in our family. Remember, only x plus k is in our family. So, question? Okay. So, yes, you could have both interpreter and anti-interpreter, but then you don't have diagonals. So this is sort of the tension. So you say, well, and how do we apply it? Well, first of all, something a little bit. If we have a diagonalizable family, we will call it composable. If there is some function, okay, let me explain in English, and then we'll read it. Remember function plus 1. What is so good about plus 1? It's not fixed point. For any x, x plus 1 is different from x. Do you agree? Now, I don't want to restrict myself to plus 1. I want to say, give me some function such that I could move things to some, it could be not. It could be any non-fixed point function. And composable family is a family where every binary function is composable with this non-fixed point. Right? For example, an example, I could just add 1. But I'm not restricting. I'm saying there is such a function. This is what, this is how you get abstract by saying, I don't say it's plus 1. I say it's anything with the property I want. And what's the property I want? F of x, this is Gothic f. Gothic f of x is not equal to x. That's the property. This is the only property of this function. How many functions like that do I need? 1. So in the family, I have this ability that if something like w is in the family, the composition is also in the family. Right? You will see. It all will make sense. Now, and then we have this wonderful theorem of non-existence of the interpreter theorem. we say that if we have, okay. So what we say that, I don't know where's the statement of the theorem. Is it after? No. No, I lost it. I apologize. So in this composable family, there's not a composable family with this property does not have, with this function, Gothic f, does not have an interpreter. We already proved that nothing has anti-interpreter. So let's see under which conditions there is no interpreter. And we're saying that as long as we have something like +1, we cannot have an interpreter as well. Because, why? Trivial. Because since if there were an interpreter, this is an interpreter, I could compose it with our function. And that will give me anti-interpreter. Because I'll just plug the code, and it will do whatever your function does, and then +1, which will be a different thing. So nothing which has +1. Right? So let us, again, dwell on it. These proofs are written quite correctly. So examples of composable diagonalizable families. Yeah, C-D. Total computable functions over integers. They're diagonalizable, and they're composable. There's, what is my Gothic f function? +1. Polynomial time functions over integers. Again, if function is polynomial time, its diagonal is also polynomial time. Trust me. I mean, it's just. And what's the, by the way, what's the Gothic f function? +1. Why not? Continuous functions over real numbers. Remember continuous functions? Again, continuous functions give you diagonalizable family if you have function of two variables which is continuous. Its diagonal is going to be continuous. They're not going to be jumps on the diagonal. And differentiable functions over real numbers. If you are smooth in both directions, you're going to be smooth along the diagonal. So it's mathematical. And all of these things tell us, by the way, that immediate mathematical results. Which means, for example, we know that if we look at the number of functions of real variables, cardinality of functions of real variables from real to real is greater than the number of real numbers. It's like power set. But the set of continuous functions of real variables is actually the same cardinality as reals, continuum. So there is a mapping from real functions to all, from real numbers to all continuous real functions. But according to our theorem, there is no continuous mapping. This mapping cannot be continuous. Or, and you could get all kind of wonderful stuff. So I have 5 minutes, so I need to. So Turing constructed a universal Turing machine, right? He built this program for a Turing machine, which is an interpreter for any Turing machine, universal Turing machine. And if we accept Church's thesis, such an interpreter exists in any Turing complete system. Why? Because we know that Turing, we accept Church's thesis, we know that whatever formulas you come, I could interpret my formalism in your formalism and back. Therefore, I could get self-interpreter by going through Turing machines. I mean, it's a bad interpreter, but we just need to prove the existence. All right? Then there is an interpreter thesis, which I do not know if it's provable or if it's metaphysical. is actually if any non-trivial set of computable functions has an interpreter, it's Turing complete. I have been struggling with it for decades. I still do not know. Right? But it's what I claim that ability to have an interpreter, to me, is a clear demonstration of your universality. And non-trivial is to exclude cases when you have computable functions into domain with one element. I mean, there obviously we could. I couldn't have, you couldn't have non-fixed point. You cannot have Gothic function f, whatever. Halting problem. Now what I am showing is to show you how, with all our machinery, we could solve Turing's halting problem, which appeared to be so difficult then, in one line. So there is no computable function halt, which takes code and input and tells you whether given code will terminate halts for given input. You just can never have this function. Why not? Because if you can, we will be able to construct an anti-interpreter. How? Anti-interpreter, which takes code, which takes input. What does it do? It first checks. If it halts, return interpreter. We have an interpreter. +1. If it doesn't halt, return 0. So for every input, it will do something else. It is an anti-interpreter. And we know that it cannot exist. Therefore, function halts cannot exist. Again, of course, you guys want to say it's sophistry, but well, it's scientific sophistry. See you next week.